everyone, welcome to our show, Deeper into Science, Deeper into Your Heart. Today we have invited a special guest to our show, which he's just finished his PhD level study in biochemistry and he is graduated from Oxford University in Malaysia branch. Let us welcome Dr. Wong Yi Heng.
Hi everyone, I'm Dr. Wong.
So before we start, we'll this out first.
So today our topic is about isotope.
Yes. So before you introduce to us about more deeper understanding about isotope, radioactive isotope or radioisotope is a form of an element that has an unstable nucleus has too many or too few neutrons, and it will release radiation in the form of alpha, beta, and gamma rays. Is that correct?
Yes, you are right, Isaac. So how does these isotopes evolve themselves to solve this problem? Over time, isotope will undergo some radioactive decay to become a more stable element.
But the radioactive word itself sounds like so dangerous to humans. Does it bring any benefits to us?
Well, in medicine field, actually we have an isotope called Tectanium-99m, which can be used in scanning or imaging that helps doctor to see what happens inside our organs.
Then in archaeology and geology field must be the radiometric dating, because the carbon-14 dating is used to estimate the age of the fossil, the bones, and the artifacts that are up to about 50,000 years old. Is it correct?
Yes, you are correct, Isaac.
So then how about the industry field? I still can't imagine it.
So in industry field, normally we use isotope to track where the leakage happens in the pipelines. So normally we will add some isotope inside the flow, then we will see where the isotope escape, then there's a place where the leakage happens.
So we can fix the problem as soon as possible.
Yes, you are right, Isaac.
Actually, I'm left-handed. So I think all of our audience must be boring of hearing this isotope topic. So we take a 5-minute break and we'll pass it to our partner. See you guys later.
2,000 years later.
Let's start with differentiating the structures of protein. For basic structure, the primary structure is a linear sequence of amino acids in a single polypeptide chain. Secondary structures consist of folding patterns within the polypeptide backbone, such as the alpha helices, which look like a coil spring, and beta sheets, which look like zigzag sheets. The tertiary structure is the overall 3D shape of a single polypeptide chain, formed from the arrangement of its secondary structures. Quaternary structure is made up of multiple folded polypeptide chains that come together to form one functional protein. The bonds involved in the secondary structure are hydrogen bonds between the backbone atoms only. In the tertiary structure, there are hydrogen bonds, electrostatic interactions, hydrophobic interactions, disulfide bonds, and van der Waals interactions within the same polypeptide chain occurring between the ion groups. Meanwhile, the quaternary structures involve the same types of bonds as the tertiary structure, but between different polypeptide chains. Let's move to the secondary structure itself is not function. Its main goal is to form a clear, stable locus providing the foundation for more components, ranging from protein to the basic shape of the protein. The tertiary structure determines and thus its specific function. The protein must fold into the tertiary structure and most of the proteins become functional when it is with the tertiary structure. The quaternary structure allows multiple proteins to assemble together, enabling more complex functions like cooperativity and mobility.
Okay, so now that we understand secondary, tertiary, and quaternary structures, this was important idea in protein biology. Structure determines function. Secondary structures are just basic shapes like alpha helices and beta helices, so they don't perform direct functions. They are key stable blocks that help the polypeptide to fold into its final shape. A protein can only do it well because of the specific shape it folds into. The best way to imagine this is like key and lock. If the shape of the key changes a little, it won't fit the lock anymore. For example, enzymes work because of their tertiary structure from an active site that matches the structure of them. If the folding changes a key or enzyme reaction, the enzyme can bind and the reaction won't happen. Another example is homogeneity. Its quaternary structures allow four subunits to work together to carry oxygen. If one subunit is full, the protein's ability to run oxygen decreases, and that will affect the whole body. So basically, differences in structure lead to differences in function. That's why protein folding is so important in